We're now going to turn our attention to operationalize data, the next step in the road process. Leadership of this step transitions now from the domain expert to the data engineer. There's this concept of a hierarchy of needs in AI. So as much as we want to be able to do fancy things like, object detection or write my proposal for me or tell me what I should do to make the best business that I can make, right? These like aspirational goals. There is data that needs to be done first. And at its most basic level is collecting the data. Collecting data is expensive. It often involves instrumentation. You have to be able to log it. You might have to buy sensors depending on what kind of data you're looking at. You might use external data where you have little control over how the data was collected or managed. There might be user-generated content. How are you collecting the user-generated content? Are you going to have a survey that's going to go out and ask opinions? Are you going to have cameras and make sense? Use those as sensors? The decision to collect data is expensive. It can be time-consuming. And there is a decision process on even whether you're going to collect new data or repurpose existing data or buy data from somebody. So that's the first level. The next thing you have to then think about is, okay, if I've got the data, is this a flow of data? Is this like customer data that's continually coming in and I'm buying a feed or a stream? Is this data that was collected one time and I'm going to generalize it for now and the foreseeable future? If I have flow, where am I putting it? Do I have a cloud? Do I have a on-prem hard drive somewhere? What's the pipeline for moving the data? How am I going to extract, transform, load it for use? Is it structured data where it's already in a data warehouse that's highly structured with data fields? Or is it just a mess like a data lake where there's just a bunch of data in there and there's no rhyme or reason or organization to it? When we start to then explore it, how are we going to clean it? How are we going to identify anomalies? How are we going to prepare it for analytics? When we then are going to get ready for analytics, who is actually putting the metrics and the labels and the deciding what it is and what the features are that we're going to be working with? Only then can we then start coming up with simple algorithms. Are we testing them? Are we experimenting with them? And all of that has to happen before we can really truly do AI or deep learning or machine learning. So as you can see, there's a lot of work. There's a lot under the what you see in the iceberg that has to be done in order to get data ready for any kind of analytic effort. So I think there's some key steps in operationalizing data. The first one being, do I even require perfect data? If you're doing data accounting where we are trying to automate our invoicing, we're trying to do personnel management, right, for like an HR system maybe, those sorts of accounting tasks, they require perfect data. We can't just go to a data lake where we throw, a data lake is like taking all the books off the library shelves and just throwing them into the auditorium, and you can put them in there really, really quick, but finding the book you need might be a little bit difficult, right? You don't want to do that if you have an accounting mission. But getting all the books off the shelf and being able to grab a few of them to do something about books in general, right, for decision support might be a much faster and efficacious way of doing things. When we're dealing with a lot of machine learning tasks, there's a certain level of error that is always going to exist. Just because something's happened in the past doesn't mean it will consistently happen in the future. There's error. And so maybe I don't need to have every instance. I don't need to have all of the data to make a predictive model about what's going to happen in the future. So if I'm doing decision support, I don't necessarily need perfect data. You want to have that decision point up front because it will affect the cost and time in your operationalization of data. Next question is, do I have data that can meet my needs? Is there a good proxy data? If I want to understand something about the future costs of medical billing, right? How much revenue I'm going to make so I know how much to pay doctors in a clinic. Well, I don't necessarily need to have all types of medical disciplines. I might be able to, like I don't need to look at every single surgeon's historic records of data. I might be able to take a representative surgeon from each group and generalize that a lot quicker and say, well, hey, an orthopedic surgeon is probably going to be the same as all the other orthopedic surgeons. Is that true? Well, of course not. Some people have more experience, some people don't. Some people negotiated better than others. But if I can grab one, I can actually get an analytic answer done much faster. And it might be more cost effective to get a imperfect 90% accurate solution today than wait 6 months to figure out where all the data is and get my data set. In that way, a lot of times projects spend so much time, resource, and schedule trying to get perfect data that they never actually deliver on their promise, and that leads to unmet expectations. So if we can just have that conversation up front and say, what is the proxy and what is the data we're going to use, and ask the client, the end decision maker, are you comfortable with this? I want to take a proxy data set so that I can get you an answer this week, not spend 6 months trying to get all the data done before I can actually give you any value. Do I have any partners that might share data? If I'm doing a joint venture, for example, or maybe I'm operating in an industry like my nonprofit is attempting to do AI research to help improve mental health outcomes. Well, I have a partner. We're not formally tied in any way other than a memorandum of agreement, but they provide mental health services to people recovering from addiction. So, can I get data under HIPAA consent and everything, of course, right? Can I get data from my partner that they will give me to advance my research and technology to come up with better solutions that then go back and help them out? So having those kind of partnerships where you can share data can help accelerate your development as well. I have bolded this next one. Do I need to label the data? How consistently is my data labeled? We're going to show you that when data is labeled consistently, it improves the precision of the algorithm. So when I say it's that thing, it's that thing. The volume of the data will help me identify all of the things in the data. That is an important decision, and knowing the trade-offs in that one area is possibly one of the most critically overlooked areas of operationalizing data. I would say that every manager needs to understand this point about data labeling and consistency in data labeling, and a manager needs to ask their technical team. A technical leader needs to be able to explain this point to their management team and the people working on the task. It is the most overlooked area in operationalizing data and a key reason why so many projects fail. Architecture requirements: where are you storing the data? How are you using it? How are you sharing it with team members? Right? If there's multiple people on the team, how are they getting access to it? How are you doing model version control? Where are you storing that? Do you use synthetic data? Do we understand the pros and cons of that? Do we go and acquire new data? And how do I budget for those costs? All of that kind of goes in this operationalizing data step. So we're going into more depth on data labeling. So when you're designing a machine learning model or an AI model, a lot of the applications, probably most of them, involve supervised machine learning. This is where a human has labeled the data, they're showing it to the computer so that it learns the model of what works, and then it does something with it. So one of the things that they use in computer vision to label the data is called bounding boxes. So you see in that upper left image right there, right? There is a red box drawn around the tank. There is a yellow box drawn around the person. There is a blue box drawn around the flag. There's a separate one for treads. So what we're doing in this image is a person has gone through and is labeling what the part of the image looks like that corresponds to something, and these then become features in a computer vision AI model. Similarly, for natural language processing, we might take a simple sentence, right? John bought 2 books from me that he wanted. We might do things like label the part of speech, like the nouns and the verbs and the adjectives. And we might actually look at dependency, right? Like you have to have a subject, object in sentence structure. So if we understand how the nature of language is, we can label all of these aspects and the dependency, and we're using that to kind of label it and tag it and tell it to the computer. But how consistent is that process? First of all, there's different ways in which you can label, right? So this is showing a more example, a more involved way, right? When I look at an image in the upper left, right, do I have square boxes, or do I actually go in more detail around the objects? And what you see here is, people, vehicles, various street, sky, various things, right? That's the semantic segmentation. We could look and just say, hey, I'm only interested in certain instances. I'm not interested in the roads and the buildings and the skies. I just want to look at the people and the cars. So I'm going to go and try and segment those. And there's a variety of different ways in which you can, combine these things together to label data. But however you're doing that, there is examples of good annotation and sloppy annotation. So if we look at the ability here, just say we want to make a computer vision algorithm that's going to identify the number of cars in the parking lot. Maybe this is for tracking vehicles. Maybe this is for identifying capacity in the parking lot to park new vehicles, so I can tell people where to go. But if we look at it, the goal here is that we are going to draw a box around each car. Well, I'll draw your attention to the missing labels, right? So it's showing one car was completely missed in the yellow bounding box. And if you look under the arches, there's cars that are parked into the little driveway areas there that are partially obscured, and so those are missed. So that's an example of a missing label. You can see that there's one of the dumpsters that was drawn, and that is an example of an incorrect label. You can also see the car next to the dumpster is incomplete, where the whole car isn't highlighted, only part of it. And this doesn't even address some of the issues where some of the boxes are tightly drawn around the car and others are sloppily drawn around the car. Well, those inconsistencies in the way you label those boxes affects the machine learning algorithm. A lot of times the images are not as clear. If you look to the right, this is showing you some satellite imagery. And so people can be trained to interpret the images to know what types of, in this case, boats or naval vehicles or naval ships are in a harbor. But being able to understand what's the tree, what's the dock, what's the ship, what type of ship, there's sometimes human expertise that needs to be involved in labeling in the first place. So I did an experiment where we took a bunch of images and had people label either people, vehicles, or bicycles in the images. And we had 4 annotators in an annotation center do it. And there's an example in the upper left of good annotation where the boxes are all labeled. They're consistently and tightly drawn around the people and the vehicle. And the lower left is an example of bad annotation. Now, what do I mean by bad annotation? Well, if you look at the people in the lower left, there's one box around 2 people. If you look at the vehicle that's got a red box around it, that box is kind of widely drawn. It's like a little sloppy. And so we created a metric to be able to measure how consistent these 4 annotators are in labeling the images. And we found that one annotator was different than the other 4. So the question is, what happens when you throw their data away? Well, what we found is when you throw the data away, right, the precision, so when I say it's a car, it's a car. When I say it's a person, it's a person. The precision goes up. So when we dropped annotator 1, the precision actually went up on the machine learning performance. But because we've thrown away a fourth of the data, the recall, did I find all the people, did I find all the trucks, that actually went down. So we know that precision is necessary for consistency. Now, what I would tell you is you can get significant performance improvement in AI and machine learning without doing anything different to the algorithms. In one of my other classes, I actually take data from a realtor about renters, buyers, sellers that he gets through his website, and they classify, what type of client it is. And so they get a performance in the mid 70% accuracy. By having people go back and look at the discussion chats and identify where they agree or disagree on whether a person is a renter or a buyer or a seller, and then create established standards to guide the labeling, they can go to a crowdsourcing platform and have non-domain experts relabel the data more consistently and achieve double-digit accuracy boosts without touching the algorithm at all. And so the annotation of how you consistently label your data is critical to performance. In fact, I typically find in any AI project I consult that is not performing up to expectation, the first place I look at is how the data was labeled. And if I can improve the labeling consistency, I can improve the performance of the algorithm. You see, in time, you're going to get more and more data with whatever your application is. But if you do not pay attention to the consistency up front, you are going to have technical debt you can't recover from. And this is where that domain expert and the data engineer must work hand in hand to achieve consistently labeled data so that the data scientist can actually have higher performance. There are tools in which we can help automate some of the labeling. So we can use machine learning to make recommendations. So we train a model, you take that trained model and you do automatic annotations, and you ask people to manually correct that. And you can actually take the segments with low confidence and have them correct that and leave the higher performance ones going on okay. And designing a system like this, while it's a little bit more resource intensive, will help even those experts, right? They have to have something where they're measuring the areas where they're inconsistent. And you surface that for decision. And that manual correction is either a domain expert or some other expert in the client space. And we'll talk a little bit about where that's been done in case studies a little bit later on. But it's critical. You can use technology to help automate that annotation. You don't have to just simply say, agree, right? There are clever ways you can probably come up with to highlight the examples of where people disagree and help make better decisions, and then feed that back into the process so that people are improving in the way that they label. But having an iterative process to improve the way in which you label data is an important aspect that you need to think about in how you're operationalizing your data. I'm going to take a moment here to talk about bias in AI. So bias is this idea where you might be consistent in your classification or your label or your AI task, but it might be accurate in the wrong direction. Think about you're shooting arrows at a target and the arrow keeps going in the same place, but it's not the bullseye, right? That's bias. And there's generally 3 categories of bias. The model bias is, it usually occurs like maybe you didn't include a key variable or a key factor in the model that you should have, and that's causing bias. Maybe there's some sort of weird feedback that is in the model that you've designed, and it's causing it to drift off course, or it's doing something different. Or maybe there is some sort of bias that your software developer had when they're developing the algorithm, or even a mistake that is leading to bias, right? So those are sources of model bias. In execution or in operations or deployment, you might have bias as a result of new inputs. Maybe there's something that is different in the inputs that are going into the model. I created a model for telling me about real estate prices in Chicago, and now I'm trying to apply it in Washington, D.C., right? So the input might be different. Or maybe the behavior changed. Maybe I'm looking at my real estate model from pre-COVID, and now post-COVID, people's behaviors have changed. The work schedule of work remote, hybrid work is different. People's goals or what they're looking for in a home has changed. The real estate market has shifted, right? There's differences in the environment that make that model a little bit outdated. But perhaps most of the bias actually comes in the data. We've already talked about this lack of label consistency. Another source of bias is non-representative data. When we look at gun violence, if I want to look at gun violence in Florida, what data am I going to use? There's not a lot of data collected on gun violence in Florida. I can look at Chicago. They have a really great city-level database of gun violence in Chicago, but Is the society, the culture in Florida even or representative by Chicago? There's different gun control laws and rules. There's I think it's pretty easy to get a concealed carry permit for having a concealed gun in Florida. In Chicago, it's very difficult. The demographics are different in Chicago. The levels of crime are different in Chicago. The government is different in Chicago. Well, what about the FBI Major Crimes Database, right? Well, they have national level statistics, which includes Florida. But a lot of people think that a lot of local data is not represented. There's not as much detail as there would be in the Chicago data. So these are examples where you may not have the data. You're trying to use a proxy data. Is it representative? And if it is not, there's bias, potential for bias. Are there culturally skewed data? There's a project I was doing for the IRS where when I was working with them, Stanford did a paper on bias in audits for the IRS. And their paper claimed that 17% of audits were against African Americans, yet only 12 to 13% of the population is African American. Therefore, that is an unfair bias. Well, that is an example of what I would call culturally skewed data. So if you actually look at their study, the data sample that they were drawing that from was earned income tax credits. So it wasn't all audits of the IRS, it was one particular segment. And the proportion of filers that are earned income tax credit is not known because the IRS does not retain that type of demographic data for ethical reasons. Well, Stanford estimated who was African American and who wasn't by first name and zip code. So, I mean, there's a whole set of issues that you could have with that, but let's just assume that that's okay for the minute. What you would find is that by that estimate, that flawed estimate, more than 20% of the earned income tax filers are African American. So the fact that only 17% of earned income tax credit filers were selected for audit actually suggests that African Americans were underrepresented in being selected for audit. And what's really alarming is about 80% of tax fraud is identity theft. And identity theft is largely executed against the most disadvantaged, marginalized segments of our population, because if you're wealthy and somebody steals your identity and steals your tax return, you're going to go after them. You have resources. You're going to catch them. The criminal penalties are higher. But if you're one of the roughly 25% of Americans that not only don't pay taxes, get money back from the government, right? So somewhere around 40 to 45% of Americans pay no income tax. About 25% not only pay no income tax, they get money back from the government. So not even money that they paid in. It's not a refund. It's just they get money from the government. And most of them are not aware that they have that benefit and could file a tax return and get the refund. But if you are in an identity thief can do it, and most audits are actually preventing that fraudulent payment to an identity thief. Well, if you're underrepresenting a group of people, what you're really doing is you're failing to protect a group of people from tax fraud. And so in this culturally skewed data, you can actually, the misunderstanding of the data can actually lead to a problem. So in this example of Stanford's argument about taxes and African Americans, they were not over auditing African Americans, they were under auditing. And by under auditing, they were failing to protect a marginalized group from tax fraud and help them become aware that they could actually get a benefit that they were probably unaware of. So that's another example of data bias. And then the last one is poorly cleaned data. So if you have a high level of missing values, or if the missing values are biased to a certain type of data, if you don't understand the data that you're using, that can also lead to data bias. So when we look at the concept of bias, the large majority of it actually occurs here in the data step. And the way we operationalize the data and make some decisions about data is an important area to understand. And I would argue it needs to be a conversation that technical leaders and managerial leaders have together so that they understand the risks and the limitations and they're informed in making decisions on how they do that. When we look at machine learning models, I just want to talk about, this is the place where operationalized data and algorithms intersect. I think it's important that we look at how they interact. When we look at an AI model or a machine learning model, right? When you have that word model, it is two components. There is data and there is the algorithm. Yes, you can improve the model by the algorithm, but you can also improve the model by improving the data. And so these are two components that you have to look at before you're satisfied with your model. The data, is it representative? Is it labeled? The algorithm, is it accurate, scalable, and tailored? And the model is then limited by the data and the algorithm. Well, what do we do with these models? Well, once I have a model, I can take new unlabeled data, put it into the model, and get a prediction. So the labeled data in the algorithm is going to tell me something about that past data. But because I have the model, I can now put additional new inputs into it and get a prediction or something that's prescriptive on the other end. Right? And that's basically how a model's working. And that's the role of operationalized data in that process. A model also can be limited by the volume of data. So if I look at a simple image here, right, this is a 1280 by 720 pixel image, right? So if I look at that, there are 3 channels for that image, red, green, blue. There are 256 possibilities then per channel, which gives me essentially an infinite number of variables or features, data points in this image, just this one image. And so how do I make sense of that? It'll crush even the most advanced computer will be crushed by even the most basic application of this. So one of the things we do is we don't have to work with all images. We don't need it to work for all images. We don't need it to work for all data points, right? We just need it to work for a lot of images. We need our algorithm to work for a lot of data points. And so that's how we are turning the impossible into possible. We need to make sure that we are scoping the data so that it is sufficient for a requirement and works with our algorithm. That's why it kind of falls in between the R and the A in the road process. What does that look like? Well, let's say I have too much data. Maybe I need to think about, where am I going to collect the data? Am I going to collect the data where I have an appropriate operational domain? Am I going to collect enough data so that I can get what I want? If you think of a haystack, am I throwing out irrelevant things so that I'm getting to the features that I actually need? So there's a huge process in deciding what we're doing with the data problem so that we can actually get to useful data. And if that data is imbalanced where, hey, I want to look between cars and people and I got a lot of people and I got a few cars, can I take the example cars that I have and boost them a little bit so that I kind of have more balanced data so that I can make more fair-to-fair comparisons when I'm training my model? So that type of use of synthetic data is growing more and more. I would argue that the dark blue area is where we have real data, and that's increasing as we have greater and greater collection. But what we're seeing in the future is we're going to see a rise in artificial data or synthetic data. And there's some benefits to synthetic data. One of the biggest ones is when, if I have a situation where I have rare data, right? Like here is a fraudulent event that occurs 5% of the time. Well, if I just assume that everything is non-fraudulent, that is accurate 95% of the time. That's pretty good. That's not helpful in actually discerning an algorithm that's going to identify fraudulent events. So I might want to take that 5% and create synthetic data that looks like it so that so that the machine is going to be more likely or penalized a little bit more if it fails to identify the fraudulent content. This has been a review of the operationalized data step in the ROAD framework.